Dear all, welcome to attend the No-Age and No-AD seminar series. This seminar series is co-hosted by the University of Oslo, the University of Copenhagen, the Chinese University of Hong Kong, the Norwegian University of Science and Technology, the KG Ibsen Center of Alzheimer's Disease, Carver Institute for Systems Neuroscience, as well as the two Norway-based international No-Age and No-AD networks. Professor Jon Storm Matthiesen, Manuel Waiter, Leonard Rasmussen, Wai Chen, and myself are co-hosts of the seminars. The special focuses of these seminars are on mechanistic, translational, and interventional studies on broader aging and age predisposed Alzheimer's disease. We have scheduled over 30 talks for this year, so please visit our website, www.noad100.com for more details. And today we are very honored to have Professor Dr. Ira Haraldsen to give us a talk on AI for the screening of mild cognitive impairment patients. I would like to give a brief introduction of Professor Ira Haraldsen, who is an MD, PhD, neurology and psychiatry. She had academic experience of clinical department and research group leadership. She has a research background in neuroendocrinology, neurobiology of aging, and translational innovation project management. She is a PI of a very big EU funding, Horizon 2020, with a total of 14 million euros. And she has been actively involved in both Norwegian and EU-based grants. And her lab is very productive in publications. In the last 3 years, she had published over 30 papers in the Haraldsen lab. So we're very pleased to have you, Professor Ira Haraldsen, please.
Thank you so much for inviting us and the AI Mind team. I may then start telling you a little bit about this starting project. We are just starting since March. And the idea behind is this huge gap between research possibilities and clinical use. And it frustrated me at the end of my professional career more and more that almost nothing is entering the clinic. And we are still in this field of MCI searching around like we did for 30 years ago, more or less. Meaning that in the European community, there is, based on huge investigation, which was published, I think, in Lancet, it was then restated that only 15% of the European citizens will ever get in contact with positron emission tomography of fMRI or whatever. So the standard procedures in MCI or dementia are neuropsychological testing, classical paper pencil based neuropsychological testing, which we in fact developed mainly during the 30s and 40s of the last century. And we are doing an MRI and static MRI today. And we know all together that this is not sufficient to identify early stages as all of the disease. And you especially know of course, the Alzheimer's disease is nothing which is starting when you are diagnosed or shortly before. It's a long process which will lead to this disease. And of course, you may wonder if you can call it a disease. I would prefer to call it a syndrome. There are many mechanisms behind which might be affected and might be differently affected by different etiological entities. So what happened with our project? It's a long story. We started several years ago with Christopher Hartlestad, who is as well attending and will take over some of the slides later during this presentation. And we were interested in this mapping of brain networks. And again, a research idea 20 years ago established was nothing new, but again, in clinical use, very rarely done, and when done, very much with experimental design and tremendously demanding with regard to expertise. So the idea was then, during 1.5 years, or a little bit more than 1.5 years ago, in a meeting when my research group was evaluated in Cambridge, and then we decided, this little group, we should do something, and we should in fact come to the clinic with an EEG-based brain network analysis method. This developed then to the final research application called Intelligent Digital Tools for Screening of Brain Connectivity and Dementia Risk Estimations in people affected by mild cognitive impairment. I have to admit, we had been lucky that COVID came and that we, in a sense, had to work online and had to be very dedicated and efficient, develop efficient working procedures. So I have to admit that these rare times and special times helped in writing this big application. In addition, it happened that after we were informed that we had won this call, then we had written as well an application together with Virtual Brain and Virtual Brain Cloud, which you may know better. And we then became as well, since March this year, a partner in the Human Brain Project, and I will as well come back to that. You know all these numbers, and I'm pretty sure that these numbers are underestimated, and a recent publication in Norway is adjusting the numbers. In Norway, we just recently stated that we have already 100,000 dementia people. So meaning we would have then about 200 living persons at the moment with MCI. It's also obvious that no one, as no nation, neither you may say globally, no nation will be able to adjust their healthcare budgets during the next 20 years to the demands of care if we are continuing this way. So we are forced to come out of the disease or syndrome diagnosis of light dementia, and we have to push the window into the pre-symptomatic area. As I mentioned, we are a big consortium. We have 4 principal PIs, clinical PIs. They are located in Spain, in Italy, in Helsinki, and in Norway. Then we have included a lot of other partners which are representing either here health economic competence. The European Commission has some main centers, and the Netherlands and Italy are especially good with regard to economics. And there, interestingly, I will also come back to it, with predictive modeling of introducing new technologies. It was important for this call as well to integrate not only classical academics, but include companies who are which are working with the industrialization of brain networks, EEG-based brain network analysis. And we integrated as well a professional business architecture, IT architecture company. Then the very important contribution was that the DNV, the Veritas, was as well joining the partnership, although they are carefully when they can participate in our project due to their status as a notifying body. But it is very important to have included a notifying body. I will also come back to that. And we were very lucky that we could get the attention of Alzheimer Europe, which is here located in Luxembourg, and which is then the representing almost all European Alzheimer associations. Another issue happened in parallel when we were writing. We had first the WHO organization wrote first standards of artificial intelligence in societies. Then the Economist came out with, in fact, 2 issues dedicated to focus on dementia and the challenges. And of course, then there was a white paper first in February 2020 with the guidance of artificial intelligence in Europe. And then later the year in 2020 as well, the assessments of future artificial intelligence algorithms and its evaluation and notifying. And very important, and many of you may know that as well, then the medical device regulation came as well, also as a white paper out, and it was then announced they would change the regulations already in May 2020. That had to be postponed due to COVID actions. And it is then now just around the corner this year, and it is an important game changer because artificial intelligence algorithms are now considered as medical device class 2B and have to be approved. This having in mind, that was also one of the major reasons why DNV wished to participate, because they do not have so much experience at the moment with notifying algorithms. And we, of course, are as well as researchers not always used to the high level of documentation before introducing a medical device. Interesting, I mentioned that, is that you can already anticipate what your impact will be from a position of HTA knowledge and theory. And we were hardly working on it on these with our experts on these numbers, and if we are right and if we are succeeding, then we would know that we would, and this is important, expect a significant change of the curve with regard to costs. We are not interested in our mind solving the AD problem. We are concerned and dedicated to participate in lowering and prolonging and having an impact on costs. This would be the wonderful or the positive view of the state of the art at the moment, that you are as a patient somewhere here identified in during your MCI state. That is not true in Europe. It is only true for some countries. The Northern European countries statistics by identifying people relatively early in their MCI state. But it has as well to be underlined that in fact, also in Norway and the other Scandinavian countries, it takes a patient 8 to 15 years from reporting first symptoms to getting a diagnosis. And mainly, I would suggest the diagnosis is just here between MCI and dementia. And as we know, that is too late for intervention. It is also true that this is in the European community far away from being true in some of the countries. And in fact, Italy is the country with the highest incidence of dementia in the European community. Again, our goal was to widen up the gap. Another step has to be taken. The stigmatization of dementia and potentially its pre-stages, mild cognitive impairment, is, I would say, surprisingly normalized. And it reminds me a little bit of times far away from former times, 40, 50 years ago, when you got a cancer diagnosis that was awful and nobody wanted to talk about it. And it was always then associated to death. This is in fact true for dementia as well. It is associated to mental death, and it is associated to what should I say, all kinds of inhuman characteristics. You are missing your personality, you are missing your ability to be an equalized partner. I guess that has something to has to change, and we would like, therefore, to offer a population-based screening method like in cancer, meaning that it is highly sensitive and highly unspecific. And that is just what we wish to do. We would wish that you are coming with your first symptoms whenever they are occurring, or even better, if you would fulfill a cut-off age, for example, 50, 55, and you would go to a screening method, which would then be called our AI-Mind connector, and it would analyze, automated by artificial intelligence, your brain networks. It would then be, in addition, fed by cognitive information. And here it is again a new important point, fed by digitalized cognitive tests. Again, we are talking about the discrepancy between research and clinic. In no clinical use would a patient be offered digitalized cognitive testing today in Europe. The gold standard is still the manually investigated clinical profile done by one neuropsychologist and then analyzed manually again against so-called old-fashioned set standards. You know, when we do not have computers, then we had as well to standardize, and then we used statistics which I think are not any longer applicable today. And we will then fed in addition genetic information which is specific for, in our case, dementia-like, Alzheimer-like dementia. We are again adding something which is everywhere available. We didn't want again to offer a research in research used beyond state of the art. It's not completely true, because what we are doing is we are feeding the algorithm with information about the ApoE allele, which is pretty common, and it's state of the art. But we are also adding one new marker, P181 and or P217. These information together again in a new algorithm is then called AI-Mind predictor. And from our own research in the groups of our PIs, we know that we are in relatively small patient groups, around 100, 150 patients, may predict over 95% probability in the group of MCI if you are belonging to the 50% of risk in the MCI group or not. Maybe for those of you which are not, who are not familiar with the clinical world, MCI in bigger populations had stably shown that 50%, about 50%, will decline further and 50% not. They will either stabilize in the state of MCI or they will return to normal age correlated cognitive function. So our goal again is to identify the 50% at risk developing dementia. We have a pretty ambitious working package order. We are here working in working package 1 with the concept of governance and requirements of such medical devices, from ethics over technical specifications to clinical acceptance and economic predictions of introducing a new method. We are in working package 2 collecting information about our features to be selected either for further classical machine learning or to more advanced deep learning. We are doing both. That is also new in the world of clinical use of artificial intelligence, and it is also new, you may say, that we think as experts here in our case that the deep learning will be less biased. This is very important, and we can later discuss that. And I may remind you that of the 100% of existing AI algorithm, the vast majority is developed in China. Then the next biggest algorithm business is in the US, and only very few algorithms are developed in Europe. That was the reason of the white paper on artificial intelligence from the European Commission, and that was also the reason of going into the ethical implications and into the assessment. This is important because none of existing algorithms had been developed in Norway, and only 8 have been developed in Sweden and Denmark. That is important because you can never be better in an algorithm and the data you're giving into the algorithm. And there we start. So all kinds of human bias will be also reflected in your algorithm. Therefore, we wish to be very transparent. We wish as well to offer our data to the public, of course, and we will make it very easy for everybody to prove, to examine, and to use our algorithm. It is a hard working package, this working package 2, because you can in EEG data, for example, you can make your feature extraction almost on all kinds of levels of data. You could decide if you which kind of frequencies you're using. You could decide if you are pre-selecting from experience, from research experience, features of interest, and so on and so on. And as well in deep learning models, you could choose if you are taking human pre-selected features and applying then later deep learning aspects, or if you are giving into the machine your raw data that are demanding discussions, and they are mainly led by working package 2. Working package 3 is then the modeling, and of course there are many mathematical model possibilities for classical machine learning or deep learning, which are then led by Oslo Met and by Aalto University. The whole has to be translated to a kind of language which would be then understandable by a platform and would standardize the whole procedures. And I learned during the last month this is a huge effort, and I will as well come back to it, which kind of challenges are placed to this working package. In opposite to classical research and innovation development projects, we are doing everything in parallel. We are starting collecting human data, prospective human data, already from this year, December on. And all the clinical sites in Europe will use the same equipment. That is, of course, also a prerequisite, but it is untypical for clinical realistic circumstances, and therefore this project as well was budgeted to make that possible and to buy clinical equipment which would be standardized between the partners. I mentioned already working package 6, which is one of the most important ones, because a research project usually leads to nothing. It leads to increased insight, but it doesn't lead to a clinical change. And to make this possible, we are, as I mentioned, focusing on the health technology assessments and the proof of the concept that, in fact, for the patient and for the society, there might be or maybe positive aspects when introducing this technology. And that demands, of course, a relatively strong focus from the first day in this research project on exploitation. And that is not easy, because in this consortium, we needed already several months defining terms and wordings. Meaning in working package 2, 4, 3, and 5 was almost no agreement on what a feature is. It started there. And after a while, we decided designing a vocabulary which we could agree on and which was written down, so that nobody then could think that another expert is defining the same term differently. That was a big effort, and I think that is our big advantage today, that those people who are working in this project agreed on a terminology. Here's a little bit what I told you. That is what usually, traditionally happens and still happens. You have a research project. In the best case, the business world would take over or not take over. Then they would start product development. Then you have quite a lot of national procurement rules, if that should really be introduced or not in the clinics. And then you would start slowly with clinical validation. And if you are really convinced that this makes an effort, then you would implement it in a hospital. And then later you would finally use it in the clinics. And this traditional way took 10, 15 years to implement something which was born here as an idea. We know that we do not have that time. It is not any longer possible. The national budget in Norway is already today using 50% for health and social costs. If that is further exploding and the national budget is not expected to increase, the opposite is in fact expected, it will decrease, then we will not have the money to finance only health. We need a police, we need a court system, we need preschools and schools and kindergartens, and we need theater. So we have to have good ideas. So therefore, we put in our research project already the product development and the validation in the beginning. And the procurement would be then a very easy step if we succeed and if we prepare a good HTH working package which directly can deliver the calculations needed to the national bodies which decide on introduction or not. And then the implementation and clinical use could be tremendously shortened. What do we see already in the beginning of our project as challenges? And our main challenge, for sure, is the infrastructure. Mainly, it's not existing. And what is not existing? We are in Norway so privileged that we can offer a TSD server, as an SSD server, which is then giving today already very advanced programs on a high security server, because the data we are collecting are considered to be highly sensitive. And highly sensitive data shared between different countries are in itself difficult. It's even more difficult if you expect to introduce a deep learning approach in AI, because the deep learning demands, of course, continuously data collection, not only during the project period, but also after the project period. And although we got a very high score in the European evaluation system of our research project, they had one serious comment, and that was, how do you want to guarantee this infrastructure and as well the long-lasting infrastructure? Because we do not have to all kinds of supercomputing access in Norway, and we do not necessarily for already have ready-made the correct architecture, and we do not have stable international patients transfer standard procedures, which would then open up for different supercomputer demand processing. Menno mentioned before the meeting started the animal models. And one of our big goals is, with the e-brains and the human brain project, to make our data accessible for their collection of simulation models, because it could be of high interest later to when we have collected our data, to drive different models which are established either by animals or by bigger other human research projects, to subclassify potentially our results. A major concern is that the legal framework, which is at the moment existing, is neither matching research purposes, business, or clinical environments. And the European laws and as well the DPO guidelines in all our countries have to be reformulated as quick as possible if efficient artificial intelligence approaches should succeed in Europe. Again, 80%, as I mentioned before, of the algorithms are developed in China and the US. And we not necessarily agree with the input data and algorithm selection. I may come with an easy, understandable example. In breast cancer, I learned recently that the breasts in Northern Europe differ significantly from other European countries. I learned also that the breasts between city citizens and countryside citizens are significantly different, and so on. Your algorithm would always run in the same way over your data if it is, for example, a closed machine learning based approach. So, therefore, it is very important that also Europe and Northern Europe would deliver big data of high quality. As you may, in Norway at least, have learned during the last month, the government is planning a change of establishing a national data bank on health data. That is not so easy, and it is a very nice approach, but it is at the moment the white paper from the government is anticipating to use so-called quality data of Norwegian health data resources. I don't know if you are aware of the limitations of this kind of quality register collected data, and that is one of the biggest challenges, and I guess it will harbor that we will give up that project after a while, and we will have to have international European data banks, which could then guarantee on a completely different level big data access and quality. I personally are positively minded, because I think that the gap between research and clinical use will be minimized by artificial intelligence use, because it is forced to other kinds of collaborations and of transparent data sharing, defining, and so on. So I'm pretty sure that it will be a positive movement for all of us. It is a prerequisite, again, that we are working together with industrial collaborators, because we would not be able on all these parts of a project to contribute only by academia. The goal is, of course, in our mind to deliver a two European ethical, understandable algorithm which would be accepted by our societies and which would also be explainable for our societies. Again, we are complete depending on the TSD infrastructure at the University of Oslo. And we had already, the University of Oslo is already with eBrains discussing the interactions which would be needed to make an easy transfer between other European bigger data banks as the eBrain structure is thought to be. I have said already a lot of that our framework definition, the data understanding, what is really delivered, the data integration and the different modeling would then be integrated in a complicated but modern and transparent platform design, and would then be delivered, would then hopefully lead to a commercialization at the end of the project time. It was demanded in this call that we should receive a technical readiness level 6 to 7, and some of you may know what that means. It is a scale developed by the NASA, and then a product would be ready for clinical use at a level 9. It is not considered that we are completely finished with the engineering at the end of the project. I guess most of you have followed the last or this year's change in the European research action of the Human Brain Project and of eBrains. eBrains had been originally a part of the Human Brain Project, and eBrains went over now to become a single structure entity, a business structure entity, which will then last also after the Human Brain Project is finalized, and that will be in 3 years. eBrains will become the European infrastructure for all kinds of brain data information. And during the last 3 years, the project will focus on brain networks and their role in consciousness. It will focus on artificial neural network identification, and it will establish finally eBrains as the European infrastructure. eBrains today offers an archive, simulation possibilities and analytical tools, but with a clear focus on animal data that will change. It will get as well a lot of human data transferred. To exemplify what's going on in Norway, it's only a tiny impression about how unfocused we are at the moment. We have, with regard to dementia and AI, introduction of AI in research, we have very many strategies. And I have to admit that the strategy of artificial intelligence is in fact already the most modern and best one. And it is here, although it is coming from a completely different department, they are focusing on health, and they are already explaining which kind of legal situation we have, and which kind of changes have to be introduced. And there it is important, it is mentioned that you could, in projects, establish as well a free room which is not following strictly the existing law. This is important because that opens up for AI Mind, for example, to become a part of eBrains. Again, the virtual brain and the virtual brain cloud will probably become a kind of centralized project in eBrains by incorporating AI Mind. I told you a little bit about the demands of architecture, and it is very important, maybe only to take home messages, that there have to be solutions from industrial partners to be allowed to directly feed data into input folders. That is at the moment forbidden. We are working on that, and there are possibilities. At the moment, there has to be chosen difficult ways. At all, Cantab as a business company with digitalized neuropsychological testing is not allowed to give back directly their results to Oslo University Hospital or to any European hospital. So we are working on solutions how that could happen directly onto a TSD server. And it is in research traditionally only allowed with each hospital doing their usual procedures of pseudo-anonymization and then pre-processing and then transferring data. We will not do so. We will, through the cloud, more and more feed directly onto the TSD server. And then all this kind of work preparation and data warehouse and then the analytical work is done. But it is also important that we are discussing how the output folder should look like, and if the output folder is giving the information to eBrains, or if we could make eBrains a part of this TSD server. And of course, the industrial partners are also thinking about different countries and different possibilities and delivering closed algorithm back to each hospital. But again, that would not be the ideal, and the ideal is regarding to data quality and transparency, that this infrastructure would become, in one or another way, and we are working on it, a part of that structure, which is much bigger. And I guess, Christopher, then you can take a little bit over.
Thank you. Alondra, how much time do we have left?
You have 10 minutes. Would that be enough for you?
Yeah, I can touch briefly on some of these topics. Ira has spent time covering the most important and most interesting aspects, and these are a little bit more hands-on work. It's a bit about the background of our methods, which we have used with success in my PhD project on focal epilepsy. And then I'll just give a brief primer on these functional network methodologies based on EEG. So it won't take much time. We will have time for questions at approximately 5-6 minutes. All right. So thank you, Ira, for your rundown of the project. As you have said multiple times, we are basing the AI Mind on EEG data in principle, and this is what the AI Mind connector is all about. The AI Mind connector is basically a tool where functional networks are computed from high density EEG data. That is 128 channels in the project, but hopefully this is something we can reduce in the future for clinical implementation, but that's another story. So functional networks are basically representations of functional interdependencies between different brain areas. We calculate functional connectivity between EEG signals that come from different areas of the brain. So it's basically the statistical dependence between two spatially separated signals. So we can look at characteristics from the EEG signals, such as signal phase or amplitude, and calculate what is known as functional connectivity, which comes in many forms, like the phase locking value, coherence, mutual information, and so on. But perhaps the most easily tangible statistic is the correlation. So in principle, you could use correlation, which is more usually done in fMRI research, where you have more precise spatial resolution. But what we do to increase the limited spatial resolution of EEG signals is to do source reconstruction, which basically means that we are modeling the signals and the anatomy of the brain to sort of figure out or calculate how these EEG signals would look like if they were actually recorded from the cortex and not from the outside of the brain. So in a way, mimic intracranial recordings via anatomical models. We're using what is known as graph theory, which is a branch of mathematics concerned with the description of network characteristics, so mathematical descriptions of network topology. Most of you have most certainly touched by these kinds of methods. To the right, you can see a very basic representation of a network in the form of a graph and in the form of a matrix. So this is just a simple binary network. So graph theory is a branch of mathematics that is concerned with calculating these specific topological metrics from the network matrices. We are, in general, separating between three types of networks. We have the structural ones, where we are recording mostly white matter fibers. We have the functional networks that are what we are calculating from EEG data. And you also have the effective networks, which are basically functional networks with directional assumptions. So this is just a very simple example of a network matrix where you have weighted connections between each nodes. So higher connectivity means sort of that there's a arbitrarily or there's a shorter distance between the nodes. And here are three examples of very basic but commonly used network characteristics. The characteristic path length, that says something about the mean distance between nodes in a network. We also have the clustering coefficient, which says something about the tendency of nodes to cluster together in triangles. And then we have a metric known as the small world index, which is says something about the network's tendency to define functional units or small modules that also interact with each other across distance. So the small world index says something about the how the network approaches the assumed optimal trade-off between local segregation and global integration. So we know that the brain is working in a way similar to this. And in our second paper from the first slide I showed here, we have looked at the clinical relevance for these kind of metrics in focal epilepsy patients cohort. We have managed to identify that network characteristics of specific neurocognitive networks, here represented by a default mode network, central executive network, and the salience network, that each of these networks correlate with specific cognitive test performance in these epilepsy patients. And that's really interesting, that we can actually see that the alteration of these networks in a pathological brain actually reflects behavior in some way. And there are multiple research questions that could be spin-offs from findings such as these, like how do medication alter the networks? Are there different network alterations as per the etiology of the epilepsy and so forth? So these are findings that are specific to epilepsy, but other researchers also looked into different kinds of dementia and also other neurological diseases. So as Ira has spoken out a lot about the AR-Mind connector, but this is the very basic representation of how we are going to, or will try to enhance the process of analyzing EEG data with artificial intelligence. So the connector will identify biomarkers and will use AI in both the application of EEG processing. So we will try to find to use AI to optimize the EEG pipelines from recording to actual network characterization. And we will also use AI to extract both known features of functional networks via the machine learning algorithm, but also try to use deep learning methods to look for characteristics that are not known beforehand. So these are big data, and we hope to find a useful application of deep learning of these data. So we have two different data modalities that we are going to be working with. We have the retrospective EEG data that are basically patient data from OUS, Oslo University Hospital, and also from our partners in Italy. So at the moment, I'm working on extracting 10,000 plus data from the OUS servers just to have data to work on. So we'll sort of try to use existing data, for example, to predict the age of the patient or the age group of the patients and different characteristics. But we'll also have a prospective study, which also Ira has introduced, that we will collect EEG data and cognitive data and all of this from 1,000 people with MCI, mild cognitive impairment. So that means 4,000 EEG measurements. So there's a lot of data. Yeah, so I think you have touched on all these aspects, Ira. It's important to underline that we are aiming at data sharing and open access for all of the final data banks in the project, and that the AR-Mind connector in principle could be applied to any group of patients or pathological condition. So yeah, Ira, I'll hand the word back for you for that.
Yeah, maybe only one additional aspect. We did not tell you why we choose EEGs to do so. Our goal was to develop a globally method which could be used and is affordable, accessible, and non-harmful. And this is a very big issue, because we see to COVID what that means, who is getting the vaccines and who is not having access to it. And we think that we in Europe have a big chance to develop methodologies with help of AI, which will lower inequality in medical care. And we think another issue of using EEG signals is, of course, that it is, at least for us, not known that there is another technology competitive to more or less only synaptic pathology, and all other accessible technologies at the moment would focus on other aspects in the metabolism, but we are talking about the first synaptic pattern changes and its correlation to cognitive function, and therefore opening a new window of possibilities in a pre-symptomatic way. So the goal, and the main goal, would be then to deliver a population-based screening method, just as the pap smear is for cervix cancer today, that you at age of risk would start your continuously brain health investigations, and at the moment pattern changes of significance would appear. You would then intensify the investigation by other technologies. So I guess that are we, at least in Norway and Switzerland, and we are more or less organizing the project, and you may follow us as well on social media. Thank you so much.
Menno?
Thank you very much, Ira and Christopher, for presenting this amazing project, and very interesting and challenging project. There's a few questions in the chat, and let me start with one which is general, I think, but also touches to a question that I had myself, and it relates to what you more or less wrapped up with, Ira, is why you choose EEG recordings as your main marker, in addition to using cognitive tests and genetic biomarkers. And so there's two questions that touch upon it. One is using EEG simply enough? Does it provide enough sensitivity and specificity? Have you considered other modalities? And one of the questions mentions, for example, diffusion MRI. So any thoughts about that, or comments?
Of course, yeah. Of course, you could take MRI. When MRI is as well not focusing on synaptic pathology. That is one reason. Another reason is that if you really wish to have a screening method, it must be localized with a very simple technology demanding access, and it should be done in Ghana and in China and in Norway. And an MRI needs two big facilities. It should be community-based. We did not mention that we will calculate the cutoff, how low could we go, in fact, finally in our model, to reduce the numbers of electrodes, because again, if your wish is to access a Chinese population and an African population, then you will not have necessarily 128 channel systems. And again, the MRI, the PET, is out of any discussion. You would also MRI talk about functional MRI. There are as well quite a lot of methodological challenges with regard to that. So I think it is unrealistic to introduce a screening method based on fMRI, PET, or whatever, and it would as well not be sufficient to mirror your synaptic dysfunction.
Okay, thanks. Can I follow up on that? And so that's maybe a question that Christopher can answer, because he's looking into it. So you said you were looking at retrospective data, and of course the most important part, as far as I see it in this project, is how early can you specifically and sensitively measure changes that are going to be predictive. And there has been, over the last couple of years, a number of structural studies where they look at people who are diagnosed with clinically diagnosed amnesia or dementia, and then they looked retrospectively back into when do we first see signatures in structural changes, and those changes are predictive about 15 years before the first clinical diagnosis. Do we have any data on EEG in that respect?
Sadly, no, not as far as we know, at least. So I must underline that these retrospective data are EEG data from a non-specific patient group in order to provide the AI developers with data that is similar to what they are going to get in the prospective study. But best case, we would have had data from an MCI group or have data from patients that we knew beforehand would develop a Alzheimer-like dementia years later. But at the moment, we do not have these data. There are some, Ira, perhaps you can expand on that.
Yeah.
But there are some from the UK biobank that might be applicable, but that's not a very large database yet.
Yeah, to answer Menno, your question additionally is, of course, as long as you do not have automated AI-based analysis of EEG-based network analysis, you will never answer your question, because we have data, such data on small groups in research. But again, that might be true, that might be not true. You have to show these changes stabilized independently on age. You know, you have to have a big work to do with the AirMind connector. You have to map 20-year-old, 30 years old, 40 years, 50 years old, of course, and you have to do that systematically. But suddenly, with by this methodology, the AirMind connector will be able within an hour to screen huge amounts of people. And the analysis of the brain networks is almost done so shortly that you will be able with the AirMind connector to do just what you anticipated and wished for.
Okay, thanks. There was another question that came up in the chat a little bit earlier because one of the participants had to leave. And it is whether there is any similar use or ideas to use AI on cardiovascular disease and lung disease in relation to dementia research?
That is a very good question, and it's right. The formation is on its way. In fact, cardiology is made already in ECGs as well, the same approach, and you may have read these publications. It's amazing which kind of new features are identified. The EEG will be even more complex because of all different frequencies and so on. That is one thing. And if you are anticipating if there is a correlation between vascular processes and dementia, of course, that will be the case. And again, as I mentioned, the sub grouping will, at the moment we have automatized the AirMind connector, will happen and will of course be a side product.
Excellent. So I don't see any further questions. If there are, please type into the chat. Evandro, you have a question?
Yeah, thanks Ira for the nice talk. So I wonder if this AI initiative you guys are working will be successful, like after 5 years. if you foresee the application of the AI to the clinical, if it is possible, how many percentage of time it will be saved to get the diagnosis to the patients, and how much money it may save to the clinical side?
Could you specify the last part of your question? Also, which much
so
money you think you would save?
So for example, if I feel I may have dementia, so I start to see a doctor today, it may take me like 1 month to get the results from my GP or from the clinician. And all these 1 month, I did a different test and it cost like on average $1,000 US. And after 5 years, with your AI being applied to the GP or to any hospital, then you may just giving 7 days to have a result to a patient like me. Yeah. And it may also reduce the using of the fancy machine to give diagnosis. So it will save the money based on the cost. So I wonder, based on these two sides,
yeah,
do you have any estimation?
Yes, we have estimations. As I mentioned to you, it's not only for weeks today. As I mentioned, it takes today 8 to 15 years. And usually in clinical diagnosis, you are for almost 5 years before you are finally getting diagnosis. So we are expecting, as I mentioned, a lowering. We do not expect any huge effects, but these are for national budgets of tremendous art. And of course, because if you could reduce, and it will only take a day, 2 days to finally get your results in our procedure, then you would 50% of the patients sent home, and could tell them that they should relax and not worry. And families would not be worried, and they would stay in work, which is not the case. In Northern Europe, quite a lot of MCI patients are partly on sick leave, although they may belong to the group which will not be affected of further decline. And the other 50%, I think you should be much earlier intensify the high technology approach to get then earlier installed, for example, the new Biogene medication.
Excellent. I think we should close the session for today. There's no further questions. Thanks very much, both Ira and Christopher, for presenting and sharing this exciting project. And I think that we're all gonna follow you very carefully and see what comes out of it. And so hopefully you can give us an update like halfway through or so. But for now, lots of success, and thanks again for your time and sharing your work and your plans with us.
Thank you very much. We are happy to tell you our progress, about our progress.
Yes, thank you very much.
Thanks very much, and take care.
Take care.
See you.
See you. Bye-bye.